So resume recording. All right. Welcome to Engineering 1A Surveying. Class 11. We only have, after tonight, 3 more to go. So we've made it this far. We'll just keep pushing and get to the end. Want to go over any questions you have before we start the quiz? Do the quiz, 30-minute limit. Again, unlimited attempts, but it will shut off at 30 minutes. We're going to cover, like I said, a lot of information tonight between horizontal curves and vertical curves. So everything has been culminating up to these 2 topics. This is really kind of what drives home the more of the design aspect of civil engineering and surveying's application to it. So there is surveying as a big, broad career path in itself, but the answers I got from most of you during our first introduction discussion was you're all headed towards the engineering side. So how does that apply to the practical applications of engineering? That's what we're really trying to drive home. Horizontal curves, we're going to use an example of the fish hook on 17 to go over tonight, and vertical curves. So when you go over that little hill and your tummy goes, whee! Those are the kinds of things we're going to be talking about when you dive underneath the train tracks and the bridge crosses underneath. That's the stuff we want to talk about. How do we get there? How do we survey that? And what information do we need to do that? So schedule-wise, I'm going to turn and look at my calendar here. So today is the 23rd. It is a short week with Thanksgiving being Thursday, Friday, Saturday, Sunday. Following Monday, we are having exam number 3. All right. The week after that, December 7th, I'm going to use that as review. So next week, we're going to start the exam later in the evening so that we can review any questions you have on horizontal and vertical curves, because we're not going to have a whole lot of time. We're not going to have as many class sessions. The 7th, we're going to spend the evening reviewing everything we've talked about so far so that you are prepared for your final exam, which will be Monday, December 14th. So we're going to spend that whole session on the 7th going over the review periods. All right, going over the topics. I've got some items that will get posted. The video is coming from last week. Apparently there is a limit on how much you can store on the cloud with Zoom. Thanks a lot. But other than that, hopefully my jabbering away has given you time to think about whether or not you've got any questions before the quiz. And if not, we can go ahead and get started if that's what you guys want to do.
Can I ask a question about the exam next week?
All right, it is 6:04 p.m. I will stop the quiz at 6:35 p.m. and we're ready to roll. It has been published, or it's publishing, I think, something like that. Okay, good luck. Let me know if you have questions. 15 minutes has elapsed. 15 to go. All right, 20 minutes has elapsed. Mm-mm. Five minutes remaining. 2 minutes. All right, everybody back in the land of the living? All right, we'll take all that as a yes. I'm seeing thumbs up. Okay. Yeah, I noticed that nobody reminded me that I had said I was going to limit the number of attempts last time. So, maybe I'll just take 5 points off for that. Anyway, of course, I won't do that. Any questions about the quiz?
No, no questions. It was just the last problem, at least for me. I don't know if for anyone else. It was so easy to see, and yet somehow I kept making the same mistake of failing to see the cuts in the topographic map for some reason.
Yes.
I kept assuming there was going to be a fill somewhere and tried to just make the math work when there wasn't. All you had to look at was the numbers at the corners, and you could see right away that wasn't. So I guess that was the only one. Just paying attention, especially with those maps, just being able to differentiate what's going on. But that was a good question on there to have.
That's exactly the point of that question is you see that it's this tabletop, you see that it's this terrace, and you think it's supposed to be up above. It just kind of gets stuck in your head, and you look at it, but you gotta keep an eye on those numbers. That will trip you up. Yeah, we had a job where we had to grade in front of the building. It was kind of a corner. And so we built the building and we were grading around the front of it, and it looked like there was supposed to be this big drop going towards the building, which seemed really unusual, that it would slope, that the ground would slope from the corner of the street back towards the building. And it turns out that one of our engineers had a typo. And so instead of, or no, it was reversed. Instead of this big giant mountain going back towards the building, it was actually pretty level, but because they had flip-flopped the numbers, turns out my estimate was completely wrong. But that's another story for another day. And regression therapy. All right, horizontal curves. Not expecting us to design anything of that sort just yet, but we will get there. Probably after several of us get master's degrees and then move on. But horizontal curves, forgive me if I call it horizontal angles throughout the evening. It's been tripping me up all day as I prepare. Basically, this is what we're looking at. A lot of roadways, a lot of railways. How do we get the information communicated? How do we build those? How do we know where to build them? How steep a turn is it? How far do we need to go before we change another angle? So as you see, some of these, we've got some raised elevations. We've got this S curve here, scoops all the way back around and comes up and over. So there's a lot of intricacies going on with just this particular image. So let's look at, this came from the original handout that the instructors used to give for this class when it was live in person and we were able to actually touch things and hand them to you. I guess this is page 2 of the surveying cheat sheets, the handout that's on Canvas. So one thing to watch out for is this particular drawing, the nomenclature is reversed, right? LC is supposed to be the length of the chord, C is the chord length, and L would be the length of the curve. So these are a little bit backwards, but we'll clarify what we're looking for here in just a minute. Basically, we're dealing with a radius and an angle. We're given that the radius is 250 feet. Our angle is 55 degrees. How far around that circle do we need to go? What's the shortcut? Okay. How do we find that? Drop a perpendicular, which bisects this angle here. Use trigonometry, solve for L, which is going to be 1/2 of this length if we drop that perpendicular, right? So we have our opposite, we have our hypotenuse. Solving for that, we get that this length here, whole length, is 230.9 feet. If we look at the length of the curve, okay, using those formulas, we find that the length of the curve is based on the circumference, right? What proportion of that whole circumference are we taking up with that 55-degree angle? And we see that we get 240 feet. Makes sense. That dashed line should be longer than the chord. That's what we'll be doing, just in greater detail and with actual layouts. Okay. Concept behind horizontal curves is that they are circular. So we're going to use circular properties, geometry, trigonometry, angles. That's what's going to help us. That's what we're going to use, those kinds of theories, those kinds of math. All right, so here we have our fancy little sports car. Someday, maybe. All right, getting ready to take off down this road, coming in high rate of speed. But horizontal curves are circular. So each curve is going to have a radius, which means that we inherit those properties of circular geometry, right? Tangents, radii, center points, and all the wonderful properties that go along with all of that math, okay? So here we've got 2 different curves. You can see that we've got a nice sweeping arc with the much larger circle, and we've got a little tighter turn when we have a shorter radius. We have a smaller circle, okay? So clearly the radius is going to influence greatly how sloped the curve is, right? How smooth it is, how sharp it's going to be. The angles as well, right? So if we look at the geometry, and this is kind of a rough image, but I've got my little purple arrow showing the line of sight. If we're staring through the windshield of our car, getting ready to head down this path, you can see that for each one of those curves, we've got different radii, we've got different angles, deriving that information. We also have, wait for it, you guys remember this, deflection angles. So we're looking at tangents to these circles to help define our information, to give us more details. Tell us what that angle is, that deflection angle, to get back to our path of travel, okay? So each one has an interior angle, we've got a deflection angle, and we've got a radius. Circles. Holometers. I wish I had my holometer. All right. So one thing that you'll see in the textbook right off the bat with chapter 21 is that we're going to talk about the degree of curvature and the radius of curvature. And both of those are defining how sharp and how curved that circle is, right? This diagram, you know, tattoos, if those are your thing, you know, maybe right here on the inner wrist, with all the formulas you're going to have over the years, you're probably going to get a full sleeve going. But this is going to be one that I would highly recommend cutting, pasting, make it your desktop, on your laptop, on your computer, on your tablet, phone. This is what we're going to be using. These dimensions, these variables, this nomenclature, okay? Radius of curvature, degree of curvature. There's two ways to look at that. All right. There's a chord basis, which means we're looking at line C here, which is going to cut off that arc, but we can still get the information for that arc based on the radius and the angle, right? We can use a chord basis. We can also use an arc basis, which is going to give us the length along that curve, right? Which is this red line here, the length, it's the arc length. And then there's different points that we need to reference. 3 critical points. PC, point of curve, point of contact. Point of curve is probably pretty standard, but I think if you come up with any point of something called C, you're probably fine. Point of tangent, okay? That's where we're going to stop. That's where we leave that. We come back and hit that circle again, okay? So our point of curvature is where we take off, and our point of tangent is where we return to it. Even though they're both tangents to the circle, which means they are perpendicular to a radius drawn at that point, right? We get the 90-degree angle. Okay? So as evidenced by it being drawn in there. The really important one that we're going to want is the point of intersection. Where do those two tangents meet up way out in space? Okay, really not all that far from where we are. And usually we don't talk about, we're not looking at huge arcs, right? If we did, we'd just be driving in a circle. If we were looking at very, very large angles, we'd come back upon ourselves, right? We would have to have some kind of elevation change. Think about the fish hook, all right? Going from Highway 1 headed into downtown Santa Cruz, take the fish hook. I'm assuming it's still called that. Okay. So keeping that in mind, that's what always sticks with me when I think about a radius of curvature, when I think about horizontal curves, right? The different equations, we're going to get into those. So kind of deriving where this information comes from. How do we take what our knowns typically are? Usually we'll know an angle, we'll know a length, we'll know a radius. How do we find all the different parts and pieces? And Neo, did you fall asleep on your computer? What is that number in the chat? Okay. Thought I'd ask. All right. So if we're talking about the arc length, we've got a formula to find the interior angle based on the radius. And if we're talking about the chord basis, the chord we set at a length of 100. The length of the arc we set at 100 for an arc basis. Okay. So we've got two formulas on how we get that information, both relating to this D delta interior angle. Okay. All right, another important screen, nomenclature. How do we know what we're talking about? So we're approaching from this left side over here. Yeah, I guess you'd be seeing the left side too. All right. So we have this curve, we've got the radius, and we're going to be tangential to that curve. Horizontal curves are circular, so we're going to stick with that thought process. We're keeping it simple at this point. We're not saying that the radius is going to change in the middle of our curve. It does that often, but for this point, we're taking relatively small angles, and we're saying that the radius does not change throughout that example. All right, so we have our point of tangent. We have our, not our point of tangent, we have our point of curvature where we start veering off of that straight line. So then this line comes out and it's tangential to our curve. We have our point of tangency, which is where our curve ends, we say. We have another tangent to that point where we then continue on with straight. Where those two intersect is our point of intersection. So we're going to reference that a lot. We're going to use that, and especially in surveying. So not just the design and the discussion behind horizontal curves, but then how do we use this practically in the field? How do we go out and do something with this information? So there's the distance that is your tangential distance, and those are equal, okay, both sides. C is our chord length. L is the length of our arc, length of our curve. The external distance and the middle ordinate, you may be asked to solve for those. We might need them at some point, but for the most part, during our discussions, those are probably just going to be random numbers that we would ask you to follow through on the math, okay? Delta symbol, or I for internal angle, it is also equal to the deflection angle between the tangents. Based on our right angle properties, that gives us a lot of special information, right? Everything kind of circles back on itself because of those right angles, because of the properties of our circles. Formulas. So good screen to save as well. It comes with the picture, comes with the formulas. If you can remember what each one of those variables means, you're working ahead of the group, right? Not ahead of the group. You're cruising pretty good. But you can see that the majority of our variables used to solve for most of those other variables are the radius and the interior angle. With that, we can rule the world. We're doing pretty good with all that information, right? If we need to find that medial distance, if we need to find that external distance, we can do that pretty quickly. All we need is the interior angle and the radius. All right, so arc basis and chord basis. Arc basis, we give our arc length a finite distance, 100 feet. It's kind of like when we were talking about slopes, a 3% slope. We rise 3 feet for every 100 feet horizontal distance, right? Very similar to arc basis and chord basis. It helps us make the math easy. We like to break these things down into much more simplified parts and pieces, okay? I know I'm showing my age here. One of my absolute favorite movies is the movie Clue with, oh gosh, Tim Curry, Martin Mull, Eileen Brennan, Leslie Warren, a huge cast, great cast. Tim Curry plays the butler, and he is head of the kitchen and dining room. And what does the butler do? He likes to keep things tidy. Well, that's also pretty par for the course with engineers, right? We like to keep things tidy. So by going with units of 100 feet, we can break these into much easier pieces if we have a much larger project to look at. Okay. So, all right, Kenny, you're absolutely correct. Kenny chimed in on the chat and said it is still called the fish hook. So I don't have to go and hurry and change all my slides while you guys aren't looking. And as you can see, that as we come around, yeah, let me point at the screen. That helps really a lot. As we come around, if we're headed toward Santa Cruz from Watsonville, Aptos, SoCal, it does change pretty significantly because it curves back on itself. However, what we're going to analyze tonight, what we're going to look at is this outer lane, the outer 2 lanes where we're coming from southbound 17, eastbound 17. It's hard to tell. Growing up on the side of a bay will really screw with your sense of direction. So we're coming from Scotts Valley, headed towards Santa Cruz. We want to take that exit and we want to head towards Watsonville, Monterey. Okay. So we're going to take that arc. We're going to analyze that a little bit. You see how we have, this is just a snapshot from Google Earth. And I had the box selected to see the roads. And you see how each one of those, it's broken into little segments, little straight lines. There's no curves. The computer doesn't understand how to do that curve. So it draws it in segments of straight lines. It's basically what we're going to do, only we're going to say our segments are about 100 feet each. To make the math easy, we're going to break it into something we can use, something we can work with. Okay. So I took the problem and kind of overlaid the outline of what we're going to do, what we're going to be looking at. So when we do this, we have our radius. We're given certain angles. It's kind of hidden back here, but we've got stationing as well. So we're saying from our starting point, which is our point of curvature, point of contact, come around our arc, and we end up over here at our point of tangent, okay, with our stationing on this end. Just so you can see that we have this outline kind of fits, right? We're going to make it fit when in doubt. All right. So typically what we do with horizontal and vertical curves, we break it into stationing. What's the segregation for stations? What's the breakdown for stations? You can use the chat, unmute. Perfect. Olga, thank you. Yes. Stations are 100 feet apart. Think it's a coincidence? No, it makes the math easy. It makes things easier to work with, okay? You know, we still have inches and feet, but if we can get everything else into more of a consistent system with hundreds, then life will be a little bit easier. All right. So our PC, our point of contact, is station 20 plus 54. We have another, our point of tangent is 2357. How long is our curve? I can wait.
Sorry, was I muted?
Yes.
I thought I said something. Okay. So just to get things clear, you said from, I think I might have misheard. My headphones aren't working too well, but PC is 21, right? And then I cut out and you pointed over to PT and said 23. And then the question was the whole We asking the whole curve, what's the distance?
The whole curve from our point of curve where we start, the station is 20 plus 54. Going around this curve, these lowercase L's are short little lengths, right?
Mhm.
We're going to stop our measurements at 2357. Those are our stations to start and stop. What's the total distance around the length of that curve?
So wouldn't that be like around 200? Oh, I see, Olga.
Yep.
Oh, right. Okay. Got it.
Yes. So 2357. Remember with stationing, you just kind of drop that plus sign, right? You keep the decimal point, but you drop the plus sign and look at it as a whole number. So yes, 200 stations plus 57 plus 46 gives us 303. So if we talk about breaking this, into 100-foot segments, we've got 3 segments and then one little sliver of 3 feet, 3 100-foot segments. Not quite. Because what we're going to do, if we break it into segments between stations, we're actually going to have from station 1 to 22, 22 to 23, and then we have the 2 slivers on the side. So we're going to go to whole numbers, 21 to 22, the 20 plus 54 up to station 21. Olga got that one with the 57, or no, that's the 46. Okay, so we know we have a little snippet there of 46 feet. We know we have a little snippet on the other end of 57 feet. But if we can break it into nice, easy chunks, nice symmetrical chunks, identical chunks, we only got to figure it once and then do the 2 ends. So really we're looking at 3 sets of analysis because we can just repeat that over. All right. So roadways, highways typically use the arc basis. So we're going to say that our arc length is 100 feet. Our chord length is going to then vary. It's going to be a little bit shorter than our arc length. Railways tend to go the other way. Railways tend to use the chord length. However, here's the interesting thing. When you get to those small enough angles or a long enough radius, that difference becomes very minimal, out to the hundredths, if not thousandths of a foot. Okay. So being consistent and using one method throughout your analysis, that's going to be the key. And depending on the industry preference, that's going to be the other part of it. That's going to be how you determine which one to use. So rule of thumb, highways, roadways use the arc method. Railways use the chord method. Okay. So we're going to go with the arc method on this one. So we set our arc lengths in between our stations at 100 feet. Perfect. That works out great. All right. We've been given that our interior angle is 15 degrees. So that came from our original problem statement. Now we need to find the angles for those other little sides. We know that with a length of 46 and 57, we're nowhere near the 15-degree angle to get 100. We're probably around half, right? To get about half of 100, about half of the angle. So we want to find the whole internal angle. We need to find D1 and D4. When you break it into segments that are typically numbered, so we can identify the components for each one of those. L sub 1, L sub 4, and L sub 2 and L sub 3 are equal to 100. Okay, so we're going to try and find those others. So thank you, Marcine. Yeah, that's great. All right. So we were not given a radius. How do we figure out what the radius is supposed to be? Going back to the problem that first kicked off our horizontal curves. It was just one little triangle, 2 radii. So if I wanted to find this radius,
Is it the equation from earlier? For arc basis, wouldn't it just be 5,729.58 divided by the 15?
yes, it absolutely would.
Alrighty.
Nicely done.
Thank you.
Yes, that is perfect. So if we wanted to bang it out, prove out the theory, we could dissect our chord and our arc, say that our chord and our arc are close enough, come up with an angle, come up with our radius. But for the purpose of this exercise, we're going to say 5,729.58 divided by our interior angle, which for segment 2 and segment 3 are equal to 15. That then gives us our radius. The catch with those, just like we kind of ran into that issue with the similar triangles on exam 2, watch out for what your knowns are. What assumptions did we make? Right? Mason mentioned it. With the arc length, what is our assumption? What did we break that arc into? (100 feet), right? If we look at segment 4, we do not have an arc length of 100 feet. Therefore, we cannot assume the same formula. This is just to get us the bulk of those sections. It's to get us that uniform section by saying, all right, we're going to break this into manageable pieces. Okay. All right. So next step. How do we go about finding this entire internal angle? Because we need that information in order to figure out what our deflection angle is at our point of intersection, right? Because it's the same as our internal angle. Without going out and measuring all of that information, we can do it mathematically. We can do it here on paper. Okay. All right. So to find the internal angle, we know what our radius is. Let's get back here, right? 381 and 97/100ths. Come on. All right. So we found that radius. To find that angle, we can still use that formula. We just can't assume that we're at a length of 100 feet. We have to use the full length of that whole arc, right? So we've got to look at the full formula, which is the ratio of the number of degrees to the circumference of the circle, right? So 360 over 2 pi gives us our length, what fraction of our circumference over our radius. And with that, we find out that the summation of all of those internal angles is 45 degrees 45.45 degrees. Same ratio of this D, 15 degrees to 100 feet on the arc length is the same as the whole internal angle to the whole length of the arc. I can't tell if something is burning in my house or if there's a skunk right outside. Something doesn't seem right. All right. We'll go for just a little bit longer and then I'll go investigate. All right, we're going to go through an example problem. So what information do we need? That's the bottom line behind all of this. Yeah, there's the theory, there's the concept, but let's just look at what we have to do with the math, right? We know we're looking at something like the fish hook, that transition from 17 to 1, not the other way. So we're going to break this into those 4 different sections based on our stationing. So we have our first little segment, which we found based on subtracting our stations, was 46 feet. We have our other 2 segments, 21 to 22, 22 to 23. Each one of those is 100 feet. No, they're not barking, but they're passed out on the floor. So it is a danger out here for them. All right, so then we look at the last one. We don't have the interior angle yet, but we do know that the arc length based on the subtracting our stationing is 57 feet, right? So we're going to look for the rest of the information. We're going to want to fill the rest of this in. Let's see, what did I put in here next? Oh, I went ahead and filled it in. All right, we had our cord length. I thought we were going to walk through that a little bit more. So sorry. So our cord length, going back to oops, sorry, not trying to give everybody palpitations here. Our cord length, 2 times the radius times the sine of 1/2 of the angle. Okay. We can reverse engineer that. We can back into it. We can find out what that information is that we need, right? The length times the angle divided by 100 will also give us that interior angle. So that's how we would solve for those interior angles, the deltas, to come up with our cord length and finish filling out that table, right? So the ratio of our angle to the cord, to the theoretical length multiplied out by the actual length. Always those, we're coming back to those ratios over and over and over again, right? How do we proportion a part of the whole compared to the whole? Our errors of closure. How do we distribute the errors in the angles of some of the interior angles? We distribute it back to all of the other bits of data. Same kind of thing here. We're just looking at proportions. We're looking at ratios. Scales do the same thing. Kind of coming full circle. A little scary. All right, let me jump ahead here. So we've come up with our whole angle. We've come up with our radius. We know the full length of our arcs, right? We know broken down into those 4 segments, our 2 segments where our arc length is 100 feet. And then the perimeter, the little extras on the side, we know what those arc lengths are. So the whole cord length we can find using that formula, because we know that the whole interior angle is 45.45 degrees. So we can find that information just as a double check as well. Okay. So if we look at the completely filled in table, how would we come up with the interior angle? So we're going to kind of reverse engineer this and talk it through. We're going to look at the proportions. So my interior angle is to my arc length, as my 15-degree angle is to my 100-foot arc length. Pretty much similar triangles. So we're going to use that information, and that's how we end up with our 6.9. Okay. Our arc length, 46, times our full interior angle, 15, divided by 100, which is our arc length for the other circle. You can do the same thing, taking the full 303 feet and the full 45.45 degrees. Should get the same answer. Okay. So we would just simply progress around the circle and come up with the information. Not typical, but I put in a totals so we can see how close we are. How did we end up? If you add up those interior angles, 6.9, 15, 15, and 8.55, 45, 45. So that's good. Our arc lengths ended up our 303, taking our end station, subtracting our initial station. And look how different it is for the chord length. So we're off by less than 8/10 of a foot over the span of 300 feet. Not terrible. So you see how you get kind of close, right? All right. So next up, practical considerations. We need to go out and we need to find these points. We need to mark our stations so that we can go out and build the roadway. Maybe we're going to widen it out, but we need to know where those stations are. How do we find them? We go out, we can pace off 100 feet, but if we're greenfielding it, if there's nothing out there right now, what's our point of reference? We're going to have to use some heavy duty equipment, right? Get to go play with the fun stuff. So next up, what we're going to look at, where do we set up our equipment? This little purple circle down at the bottom is the center of that circle. So if you trace all those radii back, you end up in that purple circle. Now it's a kind of a big circle, but you can see the lines. You can see the center line for northbound 17. You can see the fog line. You can see the center line, the median divider is anywhere in that circle where we really want to set up our station, set up our system. We're going to have to take a lane. We're going to have to put some lane closure out there. It's going to be kind of dangerous. There's live traffic next to us. So we want to think about where we're going to set up. Now, if we remember, we had some stationing that was kind of over in this area. And if we have our equipment set up here, what are these trees going to do? A door? A window? Remember standing in front of the TV as a kid and your dad or mom, you make a better door than a window?
Yep.
Kind of hard to see through those things.
Yeah.
Okay. So, excuse me. Practicality says, take a sip of water. All right. Let's find another place where we can set up, where we can see more of our points. Okay. We want to be able to get that alignment and hit all of those points to mark them out and locate those points. So looking at where our points are, this is a rough example because everything I just told you about why we don't want to set up on our center point could pretty much apply to where we are going to plan on setting up our equipment. And that's going to be our point of curvature, which according to this puts us right here in the middle of the off-ramp. But we're only impacting our scope of work, right? We're not standing out in the middle of live traffic and trying to work out on that curve. We're just taking that curve, pissing off all the beachgoers, but you know, other than tourist money and added revenue, they're just kind of a pain in the butt. So I just did a little quick zoom in and showed you kind of where that circle is, where we'd be setting up our equipment right there on the side of the highway. It happens. You drive by them all the time. You see people out there all the time. We drive by workers. And I don't even know if I'm supposed to be talking about this, but there was an accident on one of the construction sites for granite down in San Diego. And a car came into the closure where we had people working and a man lost his life. So if there is a way we can not put people in harm's way, we need to figure out what that is. So sorry, that was really depressing. All right, looking at setting up our equipment. How do we go about it? Where do we want to do it? I don't want to contradict anything you guys have been discussing in lab. The overall thought process is if we set up with our point of we set up on our point of curvature. So it's the start of our curve, right? And we sight in and zero out our equipment on our point of intersection. We can find that information. Okay, so that's going to be our 0 point. Then what we do is based on this angle of deflection, we can then plot out and locate our stations. We know that angle of deflection. Okay. Lucy, stop it. Sorry. So we set up on our point of curvature, we sight in on our point of intersection, locate that information, set our equipment to 0. We turn 1/2 of our interior angle to that first station, which in this case we found was not quite 15.
In between, it's a 6.9, right?
6.9 feet, perfect. Yes. Then we're going to measure the chord length, because that's a nice straight line. So if we measure out that chord length, which we also calculated to be 45.92, there's our station 21. Okay. Tricky part comes, we're going to stay set up on our point of curvature, but now we're going to try and find station 22. So we know station 21 is 6.9 divided by 2. How far do we have to turn to get, much further do we turn to get to station 22? We know that this angle here that we rotated through, that is the interior angle divided by 2. So what's the angle going to be for this? Let me make sure I'm right on this. So this is just breaking it down a little bit more, showing you what that angle is, right? That for a single section, we're going to rotate through half of the angle. But remember, the angle from our line, our point of intersection, our tangent line, back to our curve, which we're looking at over here, right? Perpendicular. Sorry, take my hand off the mouse. Okay, so our tangent line is perpendicular to our point at our point of intersection. So we know that those interior angles are going to be equal. So we add the 15-degree angle to get our next rotation, okay? And our chord length, oops, that should be a 2. We figure our deflection angle is half of our interior angle, and we move through the math that way. Couple little typos here and there.
And so what are the different uses for these tables? Like if you're going to present it, would you present incremental or would you present the cumulative data?
Both.
Both. Okay.
You'll end up using both tables.
Yeah, I was just wondering if one was clear, but it makes sense why you would use both. They both have necessary information.
You can't start with the cumulative until you finish the incremental and know what your process is going to be. And the incremental is based on paper mathematics. The cumulative is what we're going to go out and actually survey.
Okay, got it.
All right. So what you'll see on the homework are more example problems. Things along the lines of find the following variables, whichever one you're not already given. Find the stationing for your start and your stop, your point of curve, your point of tangent. You're given a the type of curve it is. Are you on a highway? Are you on a railroad? What's the radius? We've been given an interior angle. We're giving a point of intersection at a given station. Using all of our newfound favorite formulas, how do we find all the missing pieces? Go down the list based on what we know, based on what we can find out. Right? Begin at the beginning. All right. So given our knowns, I threw this little diagram in there. When we did a lot of trig, it was highly suggested that you sketch out what your givens were. What's your format? What did you know? Right? Take a look at the picture. Get some kind of relationship to what the problem is trying to tell you. If you have a given slope, draw a triangle showing your 100-foot horizontal to your vertical value. Keep that in your mind. I wouldn't suggest drawing this every single time. But again, you know, this is a handy little spot. You can put a tattoo. Just, it's up to you, okay? We know where our station is for our point of intersection. We know that that's going to be midpoint of our arc. So based on what information we have, we know that since it's a railroad, we're going to use the chord basis. which means our chord is going to equal 100 feet. So starting at the top, if we know our chord, we know our angle, we know our radius, we can find the length of the arc. Given that information, we can then find our beginning and our ending. We can find our start and our stop points. So the formula for length of our arc: the radius times the interior angle times pi, divide by 180. We've got all those parts and pieces. What would we get for the length of our arc based on this information?
I got approximately 253.47 feet. Would be feet.
It would.
Oh wait, I see what I did. I thought I had multiplied by pi and I didn't. Oops. Yep,
about
there we
3
go,
times
Mason.
that.
Right?
Yes, nice save, Mason. Good job. Yes, that is correct. 796.3.31. Yeah, I got 0.31 when I calced it out. Okay. So now that we have that length, we can do a lot of stuff, right? If we find our value for our tangential length, t, the radius, the tangent of 1/2 of our interior angle. 1/2 of that interior angle, I went ahead and put it in decimals. It was given in degrees and minutes. Depends on your comfort level, how you wanted to go about doing that. You guys know I convert to decimals. So much easier on my calculator. So then we can find our start and our stop stationing. So if we take 2,500, the tangent of 1/2 of 18 1/4, which is 9 1/8, right? Don't do math in my head. What do we come up with? Yes, thank you, Mason. 401.55. It's the same variables. We just got to plug them in fancy different ways to find the different information. So we're given those formulas, we can find our point of curvature, which is we subtract out that tangential length. So if our point of curvature or point of intersection is 123 plus 24.8, and our t is equal to 401.55, where do we end up?
Sarah, I have a quick question about the station, just for a quick reminder. So the station there, would that just be 12,324.80?
Yep.
Okay, just making sure. Thanks.
Yes. Sure. So we take the difference, like Mason said, 12,324.8, subtract 401.55. The number we get is 11,923 and 25/100ths. But if we convert that to actual stationing, what do we get?
Yeah, so I didn't get the 112. I think I did something wrong, but I'm not sure. Well,
All right, let's see. What's the
yeah,
best way to go about doing this?
yeah, I got 119. Yeah, Mason.
Okay. So, yep, Mason's on the right path here. 119 plus 23 and a quarter, 23.25. Same process to get the other end. So what we did on that first example, where we were looking at the fish hook and we went 300 feet, right? We started out with the two endpoints and took the difference. Here, we're just going to work in reverse. We're going to take the station of our first point. We calculated our total length of the arc already based on the radius and the angle we were given, 796.31. So when we add that to our point of curvature, 119 plus 23.25, what's our point of tangent? Yes. If we look at just the numbers, 11,923.25 feet plus 796.31 feet gives us 12,719.56 feet. Converting that to stationing, 127 plus 1956. Okay. I hate to say this, that's the easy part. Now we're going to break this whole thing down into the components. All right. We know we've got 796 feet. So we've got all these stations in between. We go from 120 to 127, and then the two little end caps, right? We're going to walk through the rest of this. So in your book, these formulas are all laid out. In the handouts, they're laid out. You can grab a screenshot here. I haven't posted the slide deck just yet, but I'll post that as well. So, you know, start writing on the inside of your arm, ink pen, Sharpie, whatever you got to do. All right. So like I mentioned, by breaking that down, it seems daunting. Oh crap, we've got 120 to 127. I mean, 7 different stations we got to do all this for. 8 and 9 if you count the 2 end caps. But is it really 9 different calculations? Because once we do the calculation from station 120 to 121, it is identical to all the other full stations, segmented at 100 feet increments. Okay. So the middle section of our tabulations are going to look pretty boring for the incremental portion. Let me go back to that table. See if I can do this. All right. So here we only had 2 full stations in the middle of our diagram. But this time we're going to have 7. And it's just going to repeat itself 7 times over. So that's kind of handy. Cumulative, going to be a little bit different, right? Different story there. So jumping ahead, we're going to calculate what's our angle, our interior angle for a full station from 120 to 121. We're going to calculate what our chord length is. That's all we need. In order to go survey this, we need our interior angle and we need our chord length. How far out do we go? What direction do I head? And how far do I go? Right, Lucy? Okay. And it's the same for 121 to 122, 122 to 123, 123 to 124. You get where I'm going with this. Okay. Any questions on that basis, that middle section? Good so far?
Are there any situations where that changes or? No, it's just, yeah,
The radius doesn't change. The length, we're still saying it's 100 feet because we're going station to station.
right.
No.
It's cool. I like that.
So the key to that, horizontal curves are circular.
Okay.
I've said it 3 or 4 times now.
Right.
It would behoove you to write that down. Okay. That's what allows us to use these formulas, to have this standard and to say we're going to break this into manageable chunks. The unmanageable chunks, those 2 little funky end caps or end pieces, are partial stationing. Okay, how are we going to go about analyzing that? Exactly the same way. Same process. We know what our length is because we have our stationing that gives us that difference. We can find that measurement. We know what our radius is because we found that we were either given that or we've calculated it based on one of our stations. So we can come up with what our angle is for that interior angle, 1.76 degrees. We can find out what our chord length is. Once we've found that angle, we can find our chord length. Just repeat the process for the far end. Chord length is our arc length, arc length is 1956. Gives us less than half of a degree. It makes sense. 20 feet chord length or arc length even over the course of 2,500 feet. That is not going to be a very big angle, right?
Sarah,
Yeah.
how are you getting the L value for the second and third station segments? For 119 plus for that one and 127. Where are you getting the L value for that?
The L value is the difference in the stationing. It's the distance between the two.
Oh, wait. So how is it 76? Oh, I see. Okay. So that's just the
I
difference.
was doing that
in
earlier.
the-
Don't worry.
Yeah. So it's just the difference in stations.
Yep.
Why wouldn't, so the L value that we calculated to find the end caps is different? Because is that totally different?
That does change. So the interior, we've broken into 100-foot segments.
Yeah.
But we've got remnants on either end that we have to deal with.
Okay, I see. Thank you.
You're welcome. Olga, did you have a question?
No,
Oh, okay. I thought I
No.
heard. Okay. So let's look at that third set of equations, that third calculation, station 127 to 127 plus 1956. What's the length of our arc? Our L value, what is that?
Only 19 feet. Yeah, 19.56 feet.
Mhm.
That's small compared to the rest of it. Wow.
What's the chord length?
19.56 feet. Wow. Wow. Okay. That's yeah.
Okay. So the longer the radius, the smaller the distance, the smaller the angle, the less difference you're going to have in that chord versus arc length. Becomes negligible. If you have a very large angle, it's going to make a big difference. You have a very short radius, it's going to make a big difference. All right, so that is the incremental data for our table. What did we come up with? 6 different numbers? Not bad. Now we got to look at the cumulative data. This one is going to get a little repetitive. This is where, if you're comfortable and proficient with Excel, setting up a formula to do this for you, excuse me, is probably going to help. Let's take the first station. And really all we're doing is starting at our point of curvature, going out to the first station. Then we're going back to our point of curvature and we're going out to the second station. Just adding on, going to the next station. So think about it. We've set up our equipment at our point of curvature and we're taking readings as we go around the curve. That's what the cumulative data is doing for us. It's so we can go out and repeat this information, okay? So our interior angle at that first station from 119, 23, 25 over to 120, we calculated that angle just on the previous screen, 1.76 degrees. We calculated our chord length, 76, 75. Our deflection angle is half of our interior angle, half of 176. All right. So now let's take from station 119 and go to our second point, which is going to be station 121. Our interior angle is our first angle plus our second angle. It's the opposite interior angle at each one of those tangent points, right? So we come up with 4.05 degrees. Our chord length, it's the summation of our 2 chord lengths going out to that station. So here, 76.75 roughly from that first section, that first end cap, right? Our chord length, instead of being 100 feet along that arc, was 99.913. 8/100ths of a foot. That's why we talk about precision and accuracy. Okay. Carry those digits along. I always like letting somebody else make the decision on when to round. You take that responsibility. That's probably why I didn't actually go into engineering and design. Gotta love construction. Our deflection angle is half of our interior angle. And our interior angle at that point, 4.05, 2.025. We simply start plugging that into our tables. I cheated. I don't think it's cheating if you find an easier way to do it. I went through and used Excel, added my section in, and my section is going to always start with my first number, my first station, to whatever my new point is, 120, 121, 122. And that's what my interior angle is going to be. That's what my chord length is going to be measured. So when I go out and I'm trying to lay out this curve, I've got my angle, I've got my distance. Point me in the right direction and tell me how far to go. That's what the cumulative will do for you. Okay. Questions? Given those diagrams, those formulas, the layout of what we're looking for, that's basically your homework. That's what we're looking for on this, okay? Given the bits and pieces that we know, maybe we know an interior angle, maybe we know the length of our arc, we know our stationing. Can we find the rest of the information we need to go and lay this out? Okay. The lab teaches us how to use the equipment to do what we're talking about here. What direction do I need to go? And how far should I go? Okay. We did bearings. We did distances. We did traverses. That was all the horizontal component, right? Now we're just saying we're going to smooth out some of those corners. How do we make that happen? All right. Let's take a quick break. I know it's already 8 o'clock. It's 10 to 8. Let's come back at 8 o'clock and we'll start talking about vertical curves. We'll let this sink in. Like I said, we got a lot of stuff to go over. We're hitting both of these and they're usually a single class in and of themselves, right? We lost some time with the PG&E shutdown. We're kind of making it up on this end, and we don't want to give you an exam right before your final exam. We want to have that week for review. So we're going to cram this in a little bit. We're going to cross our fingers. We're going to study hard for exam 3, but that gives us more breathing room for the final exam to really study that and really drive home those concepts, okay? And I'm hoping that's effective education. I hope nobody's listening when I say that. All right. So see you guys at 8 o'clock. All right. Pretty regrouped. Get some water, get some air. All right. Do we have everybody back? Can you guys give me a thumbs up or a wave or a fanfare or whatever? All right, cool. 4. 5. 6. All right, that's about half of us. We can do this. All right, recap horizontal curves. See, I said horizontal angles on here. Horizontal curves are circular, right? All the properties associated with circular geometry and the angles that we get from that, the radius, the interior angle, the chord length, the tangent properties. Keep that in mind. When we're talking horizontal curves, we have them in a plan view, a flat view, overhead view, and then we deal with circles. We went through the nomenclature, point of curvature, point of tangent, point of intersection, form part of our triangle. We get this little diamond shape out of our systems. We looked at the formulas, how to use our various properties, right? Given our information, most of it boils down to find the radius, find the interior angle, and the world is your oyster. Oyster, you can do whatever you need, okay? You can find all that subsequent information, create your tables for your data management, your incremental data. Let's look at each one of those pieces and break out the components. We need the length of the arc, we need the chord length, we need the interior angle. From those pieces of information, we can then assemble our cumulative data, which allows us to have that angular dimension and that linear dimension. Which direction do I need to face and how far do I go? And with that information, we can lay out those horizontal curves, okay? Lucy agrees. She thinks that's the way to go. Hang on one second. Okay, so homework on that is posted. One comes in, the other wants to go out, and there's third one's laying in the doorway and blocking traffic. Okay, so if you have questions, let me know, shoot them in chat, speak up. We're going to switch topics, kind of, sort of, switching gears. Instead of going horizontally, we're going to go vertically now, right? The thing to know about vertical curves. So this is an aerial view of Highway 99 where the Union Pacific Railroad line crosses. It's right about at the Cosumnes River. It's just south of Sacramento, a little south of Elk Grove. So as you might be able to tell by looking at the shadows, we have an overpass here where the highway goes over the train tracks, and we have an underpass on the other side of the highway where it goes underneath the train tracks. I've mentioned this job before, and this is the one that my company's working on. What they're doing is they're putting the highway over the top of the train tracks on both sides. So they're having to build out the other side, build out the shift traffic over to, let's see, that would be the east side, build out the west side, and then put the two together, okay? So that's what they're looking at doing. And that's what vertical curves will do. Go up and over, go down and under. Different types of vertical curves. So the little pink star just shows you where that perspective was taken, where the different shots were. So roughly on the left-hand side, where we're looking at the plan view, you see that we're just to the side of the train tracks, just on the south side. So we're looking north in the profile view where we're seeing the vertical components. And you can see that the road dips down and goes underneath. Okay. So vertical curves, different from horizontal curves, which are circular. See, this is where a classroom where you could all chime in and say it all at once would have just been like really powerful and special. Instead, horizontal curves, we're dealing with circles, the math and the trigonometry, the geometry behind all of that, right? All the properties that go with it. Vertical curves, on the other hand, are parabolic. I was hoping to never see that word again after I graduated. Not the case. It's come back to bite me. So we're going to talk about parabolas. What we have is the dark blue line. We've got our ground profile. Okay. And what we're doing with vertical curves is smoothing out those components, smoothing out the ups and downs to give it a nice flow, nice even flow. Again, this might be kind of a generational thing, but lowered cars, right? How low can you get your truck? How low can you get your Chevy S10? You know, what kind of ground clearance did you have? And the lower, the better, right? That was the thing that was popular. The problem was when you went to leave a parking lot that was graded to drain. The one that I always remember is the parking lot at 41st and Capitola Road, right across from the mall. There's a Whole Foods there now. There's a drugstore, CVS, a McDonald's, like the only McDonald's left that does not have a drive-through, I think. Coming out of that parking lot, it's a steep parking lot. Its grade is pretty steep coming out to hit 41st Avenue. And when you went to leave that parking lot, if you were in a lowered car or lowered truck, you had to come at it at just such an angle, because if you came at it too steep, you were going to nosedive into 41st Avenue. And everybody behind you was going to laugh their asses off at the idiot with the lowered car that couldn't drive it and get it out of the parking lot, right? Plus and minuses. You looked cool until you did something like that. Anyway, that's what vertical curves need to be analyzed for. Can we get through there? Can we drive that? Is the slope too steep that a vehicle could not pull the grade? Okay. Depending on standard manufacturer's conditions. You go and lower a car and you can't get through pretty standard parking lots, that's on you. But if you design something like Highway 17 to where semis and delivery trucks with normal capacity and normal weight limits can't get over the hill, you've got a problem as the engineer, as the designer, right? Couple examples, I'll try and get the pictures in a little bit. The Tehachapi grade. What's interesting about the Tehachapi grade is not that it is so steep, it is that it's so long. And what it does is it's a railroad track system. The railroad comes through, the train comes through, and it actually does a complete circle and circles back underneath itself. And it's to stretch out the amount of pull that the train has to maneuver, has to manage. So instead of, you know, you've put your foot in the gas and it goes and goes and goes until it just can't go anymore. You physically cannot make more power. That's what happens to the trains. If you give them too long or too steep of a grade, you've got to give them some way to get that power back up, ramp up that power. And that's what the Tehachapi grade does. It looked at that vertical curve And the analysis was, let's turn it into a horizontal curve. Okay, so it circles back on itself. And that's what we're looking at doing here. We want to just kind of smooth out those contours, make it nice and passable. It's a place we can get through. Safe transition as well. You've probably all seen limousines, buses, very long vehicles. Trying to think of what the road says, what the sign says on the grade. Give me just a second here. Let's see if I can find it. But when there is a high spot, like train tracks, right? They come up too sharp, too steep, and come back down too quickly. Vehicles can get high centered on that, right? So that's something else we got to watch out for when we're designing. Up here. I think that's right here. Let me exit Street View for a second here. Come on. I think it's this intersection here, which doesn't look like much of an intersection at this moment, but hopefully it will. No, maybe I'm lost. I must be lost. Oh, well, I'm sorry. Thought it would be cool to see. There is a section out here. So we're looking at Cortland, Hood. Maybe it's right here. But there's train tracks that has a sign warning drivers and warning trucks. I mean, you can see we're in agricultural areas. There's trucks and trailers hauling cows and horses, and there's, you know, livestock being moved from one place to another. There's agricultural products, there's soil, there's produce, all being moved. And when you have those grade separations like that, a lot of times you've got to give those warnings that they can get stuck. Actually, I think that's I-5. Maybe it's right here. I know, rabbit hole, sorry. Nice road, huh? Couple little patches. Yep. Whee! All right. So you see that there's a yellow sign. We're coming up on the train tracks, and you see how you can see it come up. Of course, it's going to be a little hard to read the sign, but basically they're giving you a warning that trucks can get high centered. Watch out for that grade. They tell you to take a detour. So that's actually an arrow pointing down the other road. All right, so interesting little detour there, I'm sure. Again, we're dealing with tangents. Only this time we're dealing with the vertical components of them. Instead of being horizontal in a plane view, we're now dealing with vertical components in a profile view. Because if you look down at the top of a map without contour lines, we're not seeing a whole heck of a lot. So we tend to look at the profiles for vertical curves. Maps. What do the plans look like? Plan and profile view. So we need to give people a perspective. Othello, your comment about the quiz. Looking at the grades, what's going on? Identifying, do we have a hill? Do we have a depression? What are we building? So we can look at these kinds of contours, the big bold numbers, and say, okay, well, this is tapering off down the hill, right? But we're looking at elevations of about 600, 610 here, much more spaced out, right? But we need to see where this line is going relative to everything else around it, because otherwise this profile boring as heck, right? We have an existing grade. We have the line we're going to be building. We've got some elevations. We've got a couple little call outs. Doesn't tell you a whole heck of a lot what we're doing. But those two pieces of information together really tell the story. Okay. We are coming down the middle of a roadway. You can see the roads in here. They're identified. You can see intersections. You can see building plans. It's called out that this is a marketplace. So you know that that's going to be some kind of a shopping center. We've got our stationing in the profile view. In the plan view, we're just seeing the profile here, right? Or in the profile view, we get our vertical components. Pay attention to the scales, right? So down below, our horizontal scale is 1 to 100. Our vertical scale is 1 to 50. Here, this is 100 feet. That looks like a lot bigger than 1 inch. So our vertical scales, our profile scales are different as well, vertical to horizontal. Okay. Watch out for the scales. That will bite you at some point, hopefully not too badly. All right. So we have our existing grade and we have an item here. So a little bit of background, and I actually snagged this from last year's presentation. So Marcine, you've seen this. This is the San Vicente pipeline down in Southern California and outside of San Diego. This was constructed over the course of about 3 years. It was 11 miles of water line for a cost of about $205 million. The catch here was that instead of opening up the trenches, what they decided to do was use a tunnel boring machine. Total Recall, the original one. I'm seeing all these movies today. In the original one, there's that machine that is coming after, I don't even remember, Quaid and Melina, something along those lines. Anyway, they're in these tunnels underneath Mars, and there's this boring machine coming at them, all these little drill bits and all these things spinning, and it's gonna, you know, basically a horizontal blender. That's what the kind of what they used for this project. The depths of this line, you can see here that we've got an elevation of 600 feet. At this point, our pipe is down at 450 feet. We're over 100 feet deep, almost 150 feet deep. That's down there quite a ways. This pipeline ranged from 50 to 600 feet below grade, below existing grade. The diameter, you can see they've got a call out here. I don't know if it shows up really clearly. It's a 102-inch inside diameter, ID, inner diameter, SVP, San Vicente pipeline. I don't know what the material was. They're not calling that out. But that's what we're looking at here. Okay, so we're going to pick on this one section, the clouded section. It's got a call out. We've got some information here. There's a note down at the very, very bottom that says vertical curves calculated at center line of pipe. Well, 102-inch diameter pipe, 8.5 feet, right? We're not expecting it to vary a whole heck of a lot, but it could, because roadways are built with a 2% slope going to either side. Then we're looking at the roadway that's increasing in elevation. So if we're at 610 elevation over here, here's 620, down here is 570, 540. We know we've got some incline there. We can see that in the profile of the existing grade. Okay. So little detour, little education, little history. Let's zoom in and look at that area. What do we get? Okay. It's calling out for a vertical curve. Very, very similar to the horizontal curves, PC, point of curve, PT, point of tangent. They threw a V in there so that we knew that it was a vertical curve being referenced. So without the V, assume horizontal. With the V, it's a vertical curve. Okay. PVI, point of vertical intersection of our tangential points. So we're going to be looking at basically the same kind of information, right? We're going to have a curve. We're going to have tangents that come off of that curve, meet at a point, at a midpoint, and give us additional information, allow us to make those calculations. Okay. So we have a point of vertical curve, our starting point, we're given the stationing, we're given a slope, an initial slope coming in. That would be equivalent to our radius and our angle, right? Gives us 2 dimensions. How far am I going? And then what's my vertical component? We have our midpoint, our point of vertical intersection of our tangential points, and our point of vertical tangent. So we've got our last station here. We're still increasing. Notice that both of those slope values are positive. One's just not as positive. So we've got a 2% slope. I know I'm exaggerating this. And we have a 0.2% slope. Okay. So there's a break in the slope there, but it is a vertical curve. All right. Nomenclature of our curves. We have a beginning, or the beginning of our vertical curve, point of vertical curvature, ending vertical curve, point of vertical tangency. These are measured in stations, just like we did with the horizontal curves. Okay. Point of vertical intersection, where do our tangents meet? And as you can see on this diagram, we're not dealing with a constant radius anymore. We're basically dealing with 2 different slopes at the beginning and the end of our curve. We have our tangent grades. These are going to be in percentages. So when I kept giving you guys problems and questions and quizzes and exams about calculating slopes, percent slopes, and how to handle that, this is why. Okay. It's coming full circle. A is basically the change in grade. So in this example, we've got one grade that's coming up this way. We've got another grade that is negative in value. So if we were to take the difference between those two, my second grade is a negative value. I'm subtracting out my first grade, which is a positive value. Negative and negative give me another negative value. So I know that overall, I've got a negative slope happening here. L is the length of the horizontal curve. With those values, with that information, there's different types of curves to talk about. So I took that same image. When it goes up and then back down, that is a crest. That's a type 1 crest. If it goes down and back up, it is a type 3 sag. Crest, sag, okay? Now, the difference is there are 2 more types of curves. There is another type of crest, a type 2, which either goes up and keeps going up or flattens out, but basically it doesn't come back down. So it's half of a hill. The other side of that crest Because if you're at the top of the hill, coming back down. Okay. Over short periods of space, kind of what we're looking at. We're not talking, globally, everything that goes up has to come down at some point, right? Contour lines are always closed. Anyway, then there's sags. Type 4 means it goes down and stays down. Yeah, goes down and stays down. Okay. So how do we use this information? With the horizontal curves, what we were looking for was how do we lay this out? How do we indicate what needs to happen? What's going to be our points of interest? What's our stationing? What's our elevation at our stationing? Where is it located? Here we're dealing more with distance and elevation. So more like differential leveling, okay? Alignment is horizontal. Here we're dealing with vertical curves. We're dealing with more linear information, okay? Vertical, up and down, elevations. So if we were to take our same little screenshot, we're looking at this, we've got a positive slope and a positive slope, even though we've got a break in the middle. It's two positives. So what kind of curve would we say that this is? Is it a crest or a sag?
It's to be a crest.
Absolutely. So based on what I mentioned before, two types of crest. The type 1 goes up and comes down. The type 2 goes up and stays up. So based on this location, based on this area, what would we say that is?
Would that be a crest type 2? Because it goes up and stays up.
Yes, absolutely. Okay. Because of both of them having positive slopes. If you have a positive and a negative, you know that you're going up and coming back down. If you have a negative then a positive, you know you've got a sag type 3. Okay. What is the horizontal distance of this curve? So what's our L value? Might be a little, We have a starting point and a stopping point. Okay. Not quite, pretty close. Very close, Olga. What we want to do is take the difference between our point of vertical tangency and our point of vertical curvature, which is going to give us 97.97 feet. 2 feet, 3/100ths shy of 100. So here's where we start getting into conceptual kind of think it through. The question is the actual length of the pipe for this horizontal curve, for this specific one, is it longer or shorter than the distance of the curve? So if I have a curve, I have a horizontal distance. Absolutely, it is longer, okay? We're not talking very long, we're not talking very steep slopes, so probably not a whole heck of a lot longer. But basically what we were looking at with the length of our arc and the length of our chord, that's kind of what we're doing here, only in a profile view instead of a plan view. Okay. So if I had a sag, am I longer or shorter?
Wouldn't it be shorter?
A little bit shorter
Yeah.
would be the expectation. Okay, so in this case, we're talking a little bit longer. Since we got into the equations for horizontal curves, we now 2 pi r squared, stuff we knew. Now we get the equation of a parabola. Again, I was really hoping I didn't have to see this ever again, but here it is, right? So our parabolic equation, y represents our elevation at a distance x. Our x in terms of vertical curves is our distance from our point of vertical curvature. Where does our curve start? Okay, that's going to be our x value. A is equal to half the rate of change of the grade. This one is confusing. Okay, so rate of change, we basically did that when we found lengths between 2 points. Going over, going up, what is the rate of change? If we look at a slope, it is a rate of change. For every 100 feet, we go X feet vertical, Y feet vertical, right? So A, we're looking at what that average is going to be. What is going to be the average slope? B is going to be our initial grade. And C is going to be our elevation measured from our datum. Remember that word? That's been a few weeks back. It's going to be our elevation at our beginning of vertical curve. Okay. So that is the formula we're going to be using. The variables we're going to substitute into that formula. So rate of change. How fast is it changing over a period? This point, we're calling it distance. Okay. Physics. I don't remember who's taking physics. Marcine, I think you said you were as well. Rate of change. I can go from 0 to 60 in my car in a certain period of time, in 3 seconds. Okay. I have a rate of progress. My velocity is how fast I am going at any point in time. But how fast am I going from 0 to 60? I'm doing that in 3 seconds. So that is my acceleration. So my velocity and my acceleration. Acceleration is the rate of change over time. Okay. Gravity is a rate of change over time. How fast is it changing? At this point, what we're talking about is our grade of our slope and our distance measured in stations. Our unit of measure is really bizarre. It is percent per station. Yeah, I know, right? Okay. So R, the formula for that is our second grade subtracting our first grade. So if this is negative, this ends up being subtracted from a negative number divided by our distance measured in stations. So what the heck does that mean? If we are given this sample problem, our first grade is a negative 3%. Our second grade, sounds really funny saying second grade all the time. Our grade 2 is a positive 2%. What kind of curve do we have?
A sag?
Absolutely a sag. Going down and then coming back up. Okay. So we have our formula that our rate of grade change over distance is the change in our two grades divided by the distance, by the length. So we have a -3, a +2. Our length is 600 feet. How many stations is that? The answer's on the right-hand side, by the way. I know you guys are all super excited, but you don't all need to talk at once. 6 stations, 600 feet, 6 stations. All right. In this example, G1 is a negative slope. We're going to keep the sign negative. G2 is a positive slope. We're going to keep the sign. So we have a positive minus a negative gives us a positive divided by our number of stations. So we get 0.83% because our top values of grades are percentages. Our unit of measure of our distance is stations. So we get 0.83% per station. We're at 600 feet, but 6 stations distance. Okay. That gives us our unit of rate of change, right? Our percent is what's our vertical component for every 100 feet divided by how many feet are we going, except instead of feet, we're calling it stations. So that's where we get that unusual unit of measure, percent per station. So we are increasing 0.83% for every station we travel horizontally. Okay. Sure, why not? No, seriously, I mean, that really is what it is. All right. Last year, the class went through this extensive derivation of this formula. We're short on time. It's already 8:40. You can take my word for it. If you really want to, you can go through the book, do the derivation yourself. Really, I'd say kind of, trust me, really all we're doing is substituting for different variables. We just figured out a formula for R. It's the change in grade over the distance. 1/2 of that gives us G2 minus G1 over 2L. In our parabolic formula, X being our distance from our starting point, plus our initial grade times our distance from our starting point, plus our initial elevation. So we have these X components, and those are contributing to the horizontal component by the percent grade that we're using. How much that's contributing depends on how far we have gone. Okay. But we've got 2 distance variables in here. We've got a length and a length, L and X. So if we say that L is equal to X, how far are we from our base point, the beginning of our vertical curvature? We have our average rate of change times our length. That should be squared. That's what was giving me so much trouble. No, it shouldn't. It shouldn't. Sorry. because if L equals X, one of them cancels, right? So it's just one L plus G1 times our length, which is this second section of the equation. And our third section stays the same. It's our vertical elevation. What's our starting point? So to find the elevation at the next point, this is the formula we're going to use. We're going to break it down into each one of its components and go through a sample problem. And you'll see when we draw out the diagram, we exaggerate the vertical component, kind of like you saw on the pipeline profile. You give yourself a little bit more, because otherwise that pipeline profile, if we hadn't exaggerated that vertical scale, that would look really, really flat, right? For the length of distance that we're going for 100 feet, we're not going very far vertically. So we want to stretch that out a little bit. We've got to make sure we communicate what we've done there. Anything that isn't a compatible scale, if length and width don't adjust accordingly or the same, we need to clarify that. We need to specify. So given our formulas, we also want to know what's the highest point. What's the elevation at our summit? So going over Highway 17, you cross over at Summit Road, right? All the little restaurants and shops that have been there forever and a day. You'll see a sign that says, you know, summit elevation. I don't even know what it is. Is it 1,200, 1,300, something? We'd like to know what that is. How high are we going to go? So how do we find the highest and lowest points? X is our horizontal distance over to that point on our profile. We have our slopes. Again, the units are in percentage. And the length is our total length in stations. So our stationing is going to give us where that point lies and what that point is. So this is going to be a typical profile that you're going to see for problems that we're going to do. What we have is this initial curve. As you can see, we're not dealing with nice, regular radii, consistent radii. We're not dealing with circles anymore. Toto, I have a feeling we're not in Kansas anymore. It was on TV last night anyway. All right, so these are the kinds of problems we're going to run into. So with the horizontal curves, we wanted to find M and E and T and, oh, I think I said E twice, and C, you know, all the rhyming letters. Here, we want to find what's our starting point, what's our stopping point. We want to station out our entire curve so we can see where we are every 100 feet, break it into our manageable chunks, right? We want to find elevations at each one of those points. And we want to know what's our max, what's our min, what's our high, what's our low, right? Reasons we would want to find the low point and the elevation at the low point. Something kind of interesting. Let me see if I can get back up here without giving anybody a heart attack. See this elevation here, the bottom of this ancient train track? The distance between any kind of overpass and the road surface underneath, in order to move heavy equipment, cargo, transports, that sort of thing, there has to be a minimum clearance of 13 feet 6 inches. So from the tires to the axle to the truck bed to the top of whatever equipment is being moved, you've got 13 feet 6 inches on most state highways in terms of vertical clearance. we would need to know that. That is very critical, because a similar overpass like that, where the train tracks went overhead on Highway 99, just further south in Stockton, there was a truck driver who had an excavator on the back of their truck. They didn't put it in the right position. They were over height and ran into the overpass. So we need to know what those values are. That's why when you're driving along and you see brand new pavement and then it suddenly stops, it's because we can't add more height to the pavement, because then we shorten that clearance. So that's one of the reasons that we need to know that minimum height, that minimum point on our sag, right? Are we going to clear that trestle? Are we going to clear that bridge? Okay. The other side of this is that train going to clear. Kind of suck when you send a train through there and it runs into your brand new bridge. Kind of disappointing. Most of the time they need to scrape it. Kenny, you're correct. So we mill it out, we grind out portions of the material in order to meet those existing conditions and maintain certain grades and certain drainage profiles. One thing you'll see here and on this side, you see that kind of lighter color? It's because the bridge decks are concrete. So we'll put asphalt on top of existing materials, and then you have this concrete transition to the concrete bridge. That's a lot harder to grind off. So usually what they'll do, and that's why you see them cut perpendicular to the center line there. It's so you can take that paving machine and start with a nice clean line and pull it ahead. Because otherwise you can see that this bridge has an angle to it. So we have to pick that transition so that we can actually build it and process the materials. All right, let me jump ahead here. Where did we go? All right, oops. So this is where, not this is where, this is one more example of where we are coming full circle with these concepts. We have stationing, we have a slope, and we have elevations. We have distance. Can we figure out where we are in time and space? That's what we're looking for on this. So we're given our midpoint of 46 plus 70. That's our point of intersection, point of vertical intersection, right? We know what our elevation is. We know what our slope is. Can we figure out the stationing? Yeah, we've got some extra information in there, but we can figure out the stationing. Based on our diagrams, we know that that point of intersection is at the midpoint of our distance. So we know that 46 plus 70 is halfway between BVC and EVC. So where does that put us? What would our beginning stationing be? What would 300 feet look like expressed as a station? Yep, good job, Othello. So 3 plus 0, 0. We're going to go backwards from that 46 plus 70 by 3 full stations, it's going to put us at 43 plus 70, backing off 3 stations, 300 feet. Okay, so that's number 1. All right, we got that. Number 2, what's our endpoint? Where do we start? Where do we stop? Same process here. Or we know our distance, we know our initial station, 600 feet expressed as a station, 6 plus 0, 0. Add that to our starting point. You guys are just waiting for me to hit the space bar, huh? It just floats in.
I'm sorry, I don't quite understand why we assume that this point of intersection is exactly in the middle. It doesn't look like it's in the middle on the picture, and like intuitively it shouldn't be because it's 2 different parabolas, no?
You're absolutely right. I'm sorry. What we do is we can take that slope. Now, hang on a second.
Did we just like make some approximations for easy calculations or something here?
Let me check on that.
Sorry, I didn't mean to confuse anybody. I'm just myself thoroughly confused.
One second.
I suppose we make some assumptions for calculations. Okay. No, it is. I believe it is intended to be the midpoint. Let me verify that. Mhm. Yes, it is half. Okay.
So it is the point of vertical intersection minus L over 2. Here our L is 600, L over 2 gives us 300. Subtracting that from our point of intersection, it does give us the 4370.
Okay.
What we're looking at is the change for every 100 feet horizontal. We're going up 3 feet. It does look a little misleading. Thanks, Kenny. All right. We're taking this at face value for the moment. We are looking at our point of vertical intersection. Intersection of our tangents is going to be the midpoint of our distance. So even, I think, Olga, what might be throwing you on this one is that it's not the high point. The vertex of that intersection is not always going to line up with the peak or the lowest point. Okay, we'll get to that too, because we have the determine the high and the low point here, which actually I realized I forgot to do on the slides. All right, so we have our first point, our next point, our ending point, 43 plus 70 plus 600 feet. Oops, wrong space bar. 49 plus 70. Okay. That's one, that's two, done with those 2 points. Okay. Station the entire vertical curve. Not too horrible. We basically did that with the horizontal curves earlier. So we know we move to the next stationing. We've got 30 feet on one end. We've got 70 feet over on the other. That gives us our full 600 feet, but we have those 2 little sections on the end. Here's the trickier part. Determine the elevations for each station along the vertical curve. This is where it gets a little tricky to wrap your head around, because you're going, wait a second, I've got some positive, so those are increasing. I've got some negative, so those should be decreasing. How do we use one formula to cover both conditions? We do. Okay. So, any questions so far on the stationing? Okay. All of this will be posted, I swear. All right, determining elevations. Let's take that first station at 44 plus 00. Oops, that was supposed to be hidden. Gonna reveal it as though it were magic. Our formula from before, remember it was R over 2 x squared plus G1, our first slope, plus the elevation at our starting point. Okay. So we needed to figure out the elevation at our starting point. Our formula for our rate of slope change over distance. G2 minus G1 divided by our overall number of stations. So G2 is a negative 2.4. Subtract our 3% grade, divide by 6 stations, 600 feet, gives us actually a decrease, and this sounds weird, it's a decrease of 0.9% per station. So for every 100 feet we travel horizontally, our grade decreases 0.9%. So for every 100 feet we go over, we're going to drop 9/10. That's what that negative 0.9% per station is telling us. Our grade is a negative 9/10 for every 100 feet. Our stations are conveniently 100 feet. Doing the math and the conversion with the units of measure gives us every station we drop 9/10 of a foot. So how did I get the station, the elevation at our beginning of vertical curve?
By the slope.
Okay, so we have the slope. What does the slope tell us?
It just tells us the percent or the grade or the station. So
Okay. What does the 3 represent?
that's just the grade or the oh right. Okay. Yeah. Grade over station. It's so rise over run because that's the grade, correct?
Correct.
Okay, got it.
Okay.
I was moving too fast. There we go. I was moving too far ahead.
No, we're breaking this down into manageable pieces,
Right.
right? That's why we put it into stationing. We give ourselves 100-foot lengths to work with. Makes the math a little easier. Even better when we're dealing with percents, when we're dealing with slopes, we know that whatever the value is of that percentage, that is the vertical component for every 100 feet horizontal, or for every station horizontal. Full station, whole stations only, right? So for every station we go, we're going to drop or we're going to increase 3 feet. Starting here and going to the right. But what if we're starting in the middle at our point of known elevation and going backwards? We know our station here is 300 feet from our beginning of vertical curve. Our slope is 3 feet for every 100 feet horizontal. So from this point here, every 100 feet I go, I'm going to go up 3 feet. So here's the first 100, I got to go up 3 feet. Here's the next 100, I got to go up 3 feet. Here's the next 100, I go up 3 feet. And at that point, I have hit an elevation of 853.48. But how far up did I go? How many times did I go up?
9 feet.
Perfect. Yes.
That part was easy.
So working backwards, what we're saying is that from that top point, we have a 3% downslope going backwards. So every 100 feet we go back towards the beginning, we're going to drop 3 feet. So at station 45 plus 70, I'm going to drop 3 feet, which means my elevation is 850.48. At station 44 plus 70, I'm going to drop another 3 feet. 847.48. Getting back to my 43 plus 70, I'm dropping another 3 feet. Gives me 844.48. So we're going to use those slopes to our advantage. That's why I put so many of those slope problems on all the homeworks and quizzes and crap. Okay. Now the numbers are already populated. Wish I hadn't done that. From our elevation at 844.48, we know that for every 100 feet, every full station, we are going to decrease 9/10. So we have 6 stations and 9/10. No. Damn it, I had this earlier. It made sense in my head.
So per 100 feet, we decrease 0.9 foot. And per, how many we have? Like 600 feet, we decrease 0.9 times 6. Would that be that?
Yes.
No?
Yes.
Okay.
But that's what's bugging me. We used the slope to find our beginning vertical curve elevation. If we use this formula to find our elevation at the end, let's run it through that formula. Okay. So using this formula, 1/2 of negative 0.9 times x squared plus our slope, 3% times x. These are in stations. 1/2 negative 9, 6 squared, negative 0.9. G1 is 3, x is 6, plus our initial elevation. So let's do some math. 6 squared is 36.9 times, but that's a negative number. Take half of that, gives me 16.2 negative. G1, we said, is 3%. Our distance is 6. That gives us 18, positive number. So take the difference there. That gives us a delta of positive 1.8. Add that to 844.48, gives us 846.28. We did the math here to find out what R was. G2 minus G1 divided by L gives us a negative 0.9% decrease per station. We're going 6 stations across using the parabolic formula. 1/2 times our value for R, negative 0.9, x squared, which is our 6 stations, say that 6 times fast, squared, 36 times negative 0.9 times 0.5. So 1/2 R times X. That's not the right numbers there. Let's go back up here. G1 is 3, X is 6 stations. That gives us 18. A negative 16.2, a positive 18, and a positive 844.48 gives us 846.28. The next formula that we have up here is looking at station 44. So this is where we're only going a small section. We're not, this is one of our end caps, right? All we have is 30 feet. So for every 100 feet, we're going to drop 9/10. But for 30 feet, how far what are we going to drop? So we're going to plug that into the formula as well. So we come up with our X at 0.3 stations. 30 feet is 0.3 stations. G1, 3, X, 0.3 gives us a rate of change over that small period, that small section of 0.9. It's a positive number this time. It just happens to be 0.9 again. Then we take the next component, 1/2 RX squared. 1/2 R is negative 0.9. X squared, 0.3 squared, gives us a negative 0.0405. Really small number. We're not talking 600 feet where we were on the order of almost 20, 15 to 20. Now we're talking little tiny distances, little tiny changes, just like the little tiny angles, right? Or really big radius. You're not going to see a whole lot of change in between those. It's very minimal. So we plug all those back into our formula. Negative 0.0405 plus 0.9, because that's this middle portion of the formula, plus our initial elevation, gives us our elevation at station 44, 845.34. Okay. So that's for the first station, 44. Let's jump ahead. When I first started breaking down this problem, I thought, okay, well, you know, the formula works with the horizontal curves as long as you just look at that one section. That is not the case when you're looking at vertical curves. Vertical curves, you are looking at the whole system, the whole curve from beginning to end. Okay, so this formula is based on starting with your beginning of vertical curve. You have to start with that stationing and that elevation. Everything is measured off of that point from there. So if we were to look at station 49, we're looking at everything back to the beginning. So we have same formula. Our value for R is the same. Nothing else has changed. Our slopes haven't changed. Our rate of change hasn't changed. Okay, so if we look at station 49, we have our beginning elevation, 844.48. We have our X value, station 49 minus 43 plus 70, gives us 5.3 stations. G1 times X, G1 is still 3. Even though we're on that side where it looks like, okay, we're on the negative slope side, we're still, the formula doesn't change. It's still G1, which is 3, times our distance, which is 5.3 stations, gives us 15.9. 1/2 r x squared, 0.5, a negative 0.9, 5.3 squared. Negative 12.64. Plugging that back into our original formula, negative 12.64 plus 15.9 plus 844.48 gives us 847.74. So I forgot to do the slide. Oops. But we have the formula for highest and lowest points on the curve. Where that is defined by the negative value of the initial slope, G1, divided by our rate of change. On this one, we've already calculated our rate of change, our value for R. We're given our value for G1. So if we take -3 divide by -0.9, what do we get? I should do the math. That's not what I got. Okay. Kenny, I'm having a hard enough night as it is. Negatives cancel, gives us a positive. 3 divided by 0.9, 3.33. 3 1/3, yes. Okay. So 3 at 3.33 stations. So just like, as I recall, chemistry was, it's about canceling out those units of measure. What do we end up getting if we have percent per station and multiply it by a station? If we have a number of stations and we divide by percent per station, we get some weird numbers, right? So our slope is in percent. G1 is a percent. R is a percent per station. Divide percent, flip the denominator, unit of measure. The percents cancel, we're left with number of stations. So it's 3 1/3 stations, or 333 feet, 0.33. 3 plus 33.33, if you want to put it in station terms, or we can say it's 3.3 stations. If we add that to our starting point, everything is measured from the beginning of our vertical curve. So adding 3.33 stations to 43.7 stations, where does that put us for our maximum altitude, our maximum vertical elevation? making everybody late.
So I kind of see where we're headed. For some reason, like I thought I understood. Can we just go back and go where we got the 3 from? I don't know why I'm stuck on that part, the name 3. When we got the 3 1/3, because I was following along and then let's see if I wrote down.
So
I lost my train of thought.
this is the formula we're using.
Okay, right.
We're finding a value for X. So it's a horizontal distance.
Mhm.
Always going to be measured from the beginning of our vertical curve.
Right.
The simplification is it's a negative slope, initial slope. Yes, Mason, it will. I'm sorry. I promise I'll get my shit together.
Okay. Oh yeah.
Okay.
So that's why I was missing. I could have done it on my own after that, but I didn't have the equals name G1 over R. I just had written down the G1L, G1 minus G2. That makes sense.
Write it on your wrist.
Yeah.
Maybe right here. I don't
Yep.
know. You know.
Sounds good. Okay,
right.
but that definitely makes more sense, and now I can see it.
So
Wow.
that gives us our distance. So we're
Right.
able to come up with our stationing. Now what we want to find out is what's the elevation at that particular station.
Okay.
For that, we're going to go back to this formula.
Got it.
1/2 R X squared G1 X. And remember, our X is 3.33, right? We're measuring it off of that beginning point, the elevation at our beginning point.
Mhm. And so this would be the same if it was a dip as well. If
Yes.
Yeah. Got it. Right. That makes sense. And then how would it work for like well, it makes sense if there was a elevation and then a dip on the same thing.
Mhm.
Yeah, then I can see how that would work. Okay. Yeah. And you just have to find the middle of where of between the elevation and the dip in order to
Well, the thing is, we're not at the midpoint, right?
okay, right.
So our midpoint was 46 plus 70.
Right.
When we add 43 plus 70 and 3 plus 33, that puts us over at 47.
Mhm.
So we're even further to the right of our
Right.
midpoint. So this diagram was a little bit screwy.
Okay, I can see why I was sort of getting confused. Yeah, that makes sense. It's just make sure that the math works and then go from the diagram to there. Okay.
Yeah.
Got it. Thank you. That definitely clears up a whole bunch for me.
All right. So in order to find out our elevation at that point, we would simply plug that back into our formula, right?
Mhm.
Our formula, 1/2, R is still the same, X is 3.33, G1 is still 3%,
Right.
X is still 3.33, our initial elevation is still the same. I'll run the numbers real quick. Really got to get better light in here. Okay, first vector is 5. Anybody else get 859.47? Sure. Okay. Recap. Vertical curves. Vertical curves are parabolic. Horizontal curves are circular. Parabola. Y equals ax squared plus bx plus c. The types of curves: crests go up in elevation and then back down, or up in elevation. Sags go down, then come back up. Plugging into the formula, remember your units of measure. They're really weird units on this: percent and station. Okay. But those 5 questions: what's the station in my beginning of vertical curve? What's my end? Where do my stations fall? Line that out, break it down into manageable chunks of 1 station units. Figure out what's my elevation at each station, what's my max, what's my min, and how far across is it? Measuring from your starting point. Okay. All right, next class, next Monday. Everybody enjoy your Thanksgiving. Have a very safe holiday. Make good choices. Next Monday, we will do a review of the horizontal and vertical curves. Since I won't be able to get your homework back to you, I promise I will get everything else back to you. Exam 3 will cover scales and sizes, topography, volume and earthwork, horizontal and vertical curves. I will also be posting some review questions, some review sheets, concepts, things to watch out for. None of the exams are ever intended to be gotchas. Really just want to make sure that you can apply what we've talked about in class to situations. Homework, I've posted both of them, 10 and 11. By next Monday, I know, but you don't have class Thursday and Friday. So reading chapters 22, which is horizontal curves, chapter 23, which is vertical curves. Office hours, Wednesday, 12:30 to 2:30, or by appointment. Any questions at all? And no, I do not have the winning lottery numbers. I'm sorry. Would not give those out if I had them. Okay. If you guys don't have anything, thank you for sticking around. I will get this recording posted, and homework's graded, and presentation PDF'd and posted, and homework solutions, and finish grading the quizzes, and yeah.
Just try and enjoy your Thanksgiving.
Oh, I will.
I hope so. All right.
Thank you. You too.
Yeah.